All right. So we have programming assignment 1. So that has the deadline is September 18. Brief introduction of this programming assignment 1. By the way, it's an overview of the socket and things like that. Yeah, we will do it next lecture, maybe explaining more about this programming assignment and also some socket APIs and things like that. Okay. So, so programming assignment 1 is about implementing file server using UDP, because this one is before you go going further on programming assignment. So this one is you create a UDP socket, so you don't need to maintain any state and things like that. So server side, you create a socket, and then basically listening whatever connection from the client, and client reading the file first, and then sending it. Okay, you guys don't need to worry about any error correction, but graduate student, you have to implement your error correction. Okay. So and then after reading the file and then sending it, then the server check those files and return it. Oh, it's success. I store it in the server. And then in order to get the file, you get that file name and you finally get it. And then also you want to list the files on the server, then you send the ls command, list, and it basically reply with the files in that directory, and then exit. Okay. So this is it's a very simple programming assignment, but this is actually needed. And also I will explain more in the next lecture what kind of socket API you have to use and things like that. And then also this detail will be posted tonight. Okay. So any question? Okay. Yeah, I will explain more in the next lecture. Okay. Yeah, so last lecture we talked about what's the internet and what's the main principles. Like one thing you guys remember, end-to-end principle, right? So what was the end-to-end principle? Okay, so network is dumb. You remember now. Okay, network is dumb, very simple. And then exactly. So end point is smart, and then you innovate, right? And another one is packet switch networks, and then I also discussed like best effort networks, best effort delivery. So what's the meaning of best effort delivery?
Reliability. There is no guarantee, but
so no guarantee. So you each network comes to its own best, and then the maybe end host need to take care of it. So that is the best effort delivery. And also we briefly overviewed this from the physical layer up to the application layer, right? And then application layer to the physical layer. And so link layer, what was the role of the link layer? Anyone remember? Link layer. Framing, delimiting, sending series of bits, right? Physical layer sending 0 and 1. Link layer is send series of bits. And also there are also the media. So for example, Ethernet or wireless, and those kind of media is actually basically the shared media, which means that we need to take care some kind of contention. Okay, when you send the signal, and then some other user or host can chip in, and then also that change that signal, right? Now how we detect and correct So that's the main topic of today's lecture. So if you can think, okay, there are Ethernet and also shared wireless, then when you send it, another user either have to wait or based on the what kind of technology you are using, there are some different way of schedule these multiple transmissions. And then also satellite, things like that. Okay, if we see this, this is more like, we have a sending node and also receiving node, and there is an adapter. It could be Ethernet or wireless adapter, and link layer protocol actually running. This is a layer 2, right? So you can think of this link layer, the Ethernet card, or 802.11, that wireless card, and the sending side that it encapsulates your data into frame with the adding header, right? And also the adding some error checking bits, and also when you're sending it, you should not overflow your receiving part. So there is some flow control also implemented in the link layer. And the receiving side, yeah, look for errors and also respond to this flow control and extract the data and then sending up to the IP layer, right? So somehow now repeating. So okay, link layer service encoding, right? You have to encode 0 and 1, and also the framing. So you're adding header or trailer. So you actually, in fact, encapsulating packet into frame, and also using MAC address instead of IP address. So IP address is in the network layer, and then MAC address is in the link layer. And also you do error detection. So because because of some signal attenuation or noise, or because of other user chip into the network at the same time, there could be some errors. So basically detect the error, and then also if you can correct it, you also can correct it. Okay. In case of correction costs more, then you may be adding more bits or some more mechanism to you can even correct the error without receiving another bit from the sender. Okay, and also flow control is pacing between sending and receiving nodes. Okay, let's see more. So as we know, link layer protocol is about encoding, framing, and error detection, or even error, correction, and also flow control. So there are, the 3 or 4 different kinds of, multiple access. So how you provide the sharing the medium together. So you have more users using shared networks, either Ethernet or wireless. How are you going to do it? So one is strict isolation. So you can think of, okay, why not we use a different channel? Okay, users, some group of users use channel 1. Another user uses channel 2 with a different frequency. Or you do round-robin fashion, TDMA slot. You give, okay, time 1, you transmit. Time 2, you transmit. Time 3, you transmit. So you actually schedule. So based on the timing. Okay? So that is somehow you divide the resource, right? You have either have a, frequency, so you actually give a different frequency to different users, or you have a time, so you give the order to when you have to send it. So that is, strict isolation. Another one is this centralized management is based on some token. So there is some kind of control unit, and then I give you the token. And then when you have a token, you have a ability to sending something. Okay? After sending it, you return token to me, and then I will pass to another one to sending it. So I'm just passing the token, and they use it, return that token. Okay? So that is a token-based approach. And also, if we don't want any of the central, control, why not we just do it from the, users or client side? So that is more like, decentralized management. That is, example is CSMA CD. So basic idea is, so this is a carrier sense and multiple access, okay? And then CD is a collision detection, okay? So CSMA is like this. So carrier sense, right? CS is a carrier sense, multiple access. So when you're sending it, you first sense the carrier. Whoever is sending, currently, so your channel, somehow there's a signal or not. If you cannot find it, you're sending it, okay? You're sending it, but still, there are, multiple people may send at the same time. Then either you can detect the collision, and then you correct it, so there's a current, the collision detection. But you may not, also know that whether, this corruption happens or not. So we will see more later. Okay? So physical layer is doing the analog to digital or digital to analog, right? 0 to 1. So we either use a tone or the duration and things like that. So physical link, okay, source node changing bit to signal, and then receiving node changing signal to bit. Yeah, because when you load into a certain medium, you have to send it as some kind of signal, right? So DA, digital to analog, analog to digital conversion. Okay, so there are, many ways to do it. And also, you may know this, because, for example, when you send 101100 and series of bits, that, okay, 1 is the, high voltage, okay? And then 0 is 0, 1, 1, 1. You may see this one for a long time. So this one is, we call non-return-to-zero, NRZ, okay? So, for example, is here 1011, this is 1, 0, 1, 1, 0, 0. Yeah, don't need to memorize. We will not have this kind of question, okay? But, and then, so there are some problem with, this non-return to zero, NRZ. So one problem is, okay, you have very long 0 or 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. So then, because, no transition from low to high and high to low, so it's actually hard to synchronize. And also, usually receiver, the keep, average of the signal it received, and then using that one to detect whether this is 1 or 0 and 1 or 0. So if you have, all 1 or all 0, then your detection may be very sensitive. Because when you detect, okay, this could be 1 or 0, this could be very, very sensitive. Okay? So then, okay, then what kind of, encoding methodology would be good? More transitions, right? Okay, 0, some transition, 1 transition, and things like that. So here, then, okay, why we need transition for, so that something for, clock recovery, and also the, long flash strings that do not produce any, transitions, and some clock drift at the receiver. So we will see then what we can do with that. Okay. So suppose that this is not the electrical engineering course. So you have a clock, and then also data we want to, send. So 1010011110, right? Okay. So as I said, mode transition. Okay. So here one, Manchester coding is okay. 1, you transit from 1 high to low, okay? And then also the 0, you transit from the low to high. So let's see. Okay, 1, high to low. Okay, 0, low to high, high to low. So 0 is always, you have to transit from low to high, right? So it's a low to high. And then also another 0 happens. So in case of NRZ, you stay there, right? Here, you have a 2 consecutive 0. You're always down in order to be, 0 is a low to high transition, right? And also 1 is high to low. So as you can see, this removes the long, string of no changes. Okay. Again, don't memorize. So, yeah, we are not learning this one, but it's good to know this and why we, recover and why, certain methodology actually better and etc. Okay. So then, efficiency, right? So when we sending some bit, okay, so here, Manchester, so 2 clock transition per bit, okay? So when we're sending it, we basically use 2 clocks, right? So one transition. So we use a 2 clock transition, which means you have a certain clock, your efficiency is 50% maximum, okay? But you may have, higher capacitor link. For example, 1 gig and 10 gig link. Then your efficiency should be much better. So that's why, 8B or 10B encoding, things like that, or 64B and 66. So here is you use a 10, and then you basically have 8 out of 10. So which means 80% efficiency. Don't need to memorize it. So in case that you have a very high capacity link, you need a better way of the encoding it, okay? Because not much loss in these links. So for wireless, you definitely cannot use this kind of encoding because you may have more losses. But in case of fiber, the physical line characteristic actually has a pretty low loss rate. So that's why we could use this kind of encoding schemes. Okay. Yeah, this is another example. 0, 1, 1, 1, 1. So this is NRZ. So if you see Manchester is more transition, so that the receiver side better maintain the clock. Okay. So any questions so far?
What part of this do you want us to know if we're not supposed to memorize it?
Yeah, I couldn't hear. Can you speak?
What part of this do you want us to know if we're not just supposed to memorize all these strategies for the test or for programming assignments? What part of this information is important?
This one? This one is actually important for the learning, the other lectures. Okay, so it's not really critical for your program assignment for sure.
Okay.
Okay. So now goes to the framing. So framing is okay. You have a certain data want to send, and then you delimiting, with the either with the sentinel or using some kind of patterns. So for example, you have certain content, and then we want to put the sentinel for identifying the starting and ending of that frame. Okay, so then. Okay, so this is the 0, 1, 1, 1, 1, 1, 0. This one is popularly used by the HDLC, so link layer protocol, that for header and then also Taylor. Okay, so then you may wonder, okay, because my frame content may have this, this pattern, right? Because my data could have this kind of pattern too. So how I can identify this is starting and this is ending, and also how I deliver my content without affecting by all these sentinels. So any idea how we can do it?
Escape sequence.
Yeah, that's true. Using escape sequence, and also we call stopping. So here, either we can put some kind of explicit escape sequence, or we change this frame content so that it doesn't have any the occurrence of this sentinel. So for example, in the data, whenever that having 5 consecutive 1, it adding 0. So that means your frame content shouldn't have any of the occurrence of this header and tail, right? Because sender always inserts 0 after 5 consecutive 1s. And then after receiving it, since we always insert 0, so we remove 0 after 5 consecutive 1. I mean, certainly at that time we also remove the starting and ending of the frame, right? I will show you some examples. And also, we can do some put header, and then also okay, so this data will start from the certain index. That also can be done. Okay. Okay. Now example. Okay, so this is a character byte stopping example. So now the sentinel is X, and then both starting and ending of the packet. And also, as you said, we put escape character. Okay, just assume it's E. Yeah.
To explain the difference between a packet and a frame?
Oh, okay, actually, good question. So it's actually basically the same, but in the link layer, we usually call frame instead of packet. Okay? Network layer, we usually say packet. Okay? It's the same thing, but it's actually different naming. Because of your header is different, right? Because in network layer, you have IP and other header here there. And then now you're adding link layer header, then we call frames. Okay? So that is some kind of different naming. Okay? Okay, so let's go back to this exercise. Okay, so there's the data. So we want to send this data, and it has, X and E. E is an escape sequence, right? In previous example is 0. So it's a X, E, X, E, X, E. So when we send it, then what we should do using this stopping? Because now you see, we have to put X, both the starting and ending of the packet, right? So that means, so now we added this X, okay? And then whenever that we have an X, then we escape it. So we put E here, and then here E, this is also we need to escape it, so E, X, EX. So E is the escape sequence too, right? So EE, EX, and this one is EE. Last X is the ending of the packet, right? So, and then when it receives it, so because, the starting and ending just, gone, right? XX. And then now you have the E occurs, you just removed E from each of the what you received. Okay, E, then X left, right? EE, one E gone, and you will have only E, and then also X, and the same way.
At the end, there is EX, and it is replaced with 3E and X. Where is that extra E from?
Oh, because this one is an escape sequence, right? So we have to put E in front here. And then X also, you have to put E.
Oh, one for each?
Yeah, one for each.
Okay, thank you.
So any question?
So you have to escape your escape characters. Also.
Exactly, yeah. You have to escape your escape character as well as your the sentinel, yeah.
Yeah. Thanks.
Yeah.
So who decides what is the escape character and?
Oh, that is a protocol. So, and then also in programming, we also use this kind of escape sequence pretty much a lot too. So, for example, I think you guys know C, right? Printf, you have a lot of, the \n and things like that, right?
Oh, okay.
In order to escape, you also, and then also you want to use the, what is that? This, some escape character. You have to put another one, right? It's actually the same. Okay. Since, we saw this byte stopping, so bit stopping is also same. So HDLC, that is one, popular link layer protocol. And it's actually using this 01111 flag in their frame, right? Frame. And then, because you may have a data having this sequence, so sender insert 0, and then, at the receiver that whenever that you have, consecutive 1, and then you remove 0 in the content. So here, one example. So you have data. So here, I actually didn't really include it because I put data, right? So basically, you have this, starting and ending, you have this flag, okay? So this is only for data. So when you're sending it, you definitely have to put this one, right? This one, and now see. So 5 consecutive 1, 2, 3, 4, 5. You're adding 0, and then also 5 consecutive 5. You're adding 0. Okay, you're sending it. So there is this, the HDLC flag at the starting and ending of this data. And now receiving it, already you take off this flag from starting and ending. And now you have 1, so 1, 2, 3, 4, 5. And then you remove 0. Because you're adding 0 after 5 consecutive 1. So when you receive it, you basically remove it. Okay? Then basically the receiver received the sender's sent, right?
0 there. And we will replace it now with 1, right?
No, even we already have a 0. That is just that data, right? Because, for example,
it's not replaced, it's pushed.
So here, right? So you have a 5 consecutive 1, and then you already had a 1, 0 here, right? But when we sending it, we always, this is a program. Okay, 1, 2, 3, 4, 5 consecutive, we all add it. So it should be like this.
Oh, so you still add 1, 0?
Yeah.
Okay.
And then when we receive it, rule, right? 1, 2, 3, 4, 5, we take out 0. Then it is, right, like this. Yeah.
Did you not add the sentinel in that because just like for space?
Exactly.
Okay.
In terms of my space, yeah.
Yeah, I gotcha.
It's hard to adding, here and there.
Yeah, I was already long enough. I feel that.
That's why I put, some data. So I didn't really put the link layer frame. Okay, so now, so when we send this kind of data using this bit stopping or byte stopping and things like that, still error occurs because, because of some thermal or electrical interference or many different reasons that, errors are unavoidable. So there are multiple ways to handle this, right? First is error detection. You detect whether error happens. And then also even you may correct them because when there is some errors, okay, I already know that this should be this way, then you may correct that, error too. So error detection, there are multiple ways, right? So for example, you transmit extra redundant information. So for example, you want to send 1010, and then you don't know when you receive it 1001 whether this is correct or not. In order to know, you may send multiple, right? So in case that when you're sending a 1010, you're also sending another 1010, and then when I receive it, okay, my protocol is saying I always have a one redundant the information. So I always need to have a 2 in order to make sure that my information received is actually correct. In case both are different, then you already know that error happens, right? So that is, transmit extra information. You basically detect errors, even though you may not correct it because you don't know which one is correct. But if you're sending more, you even can correct. So for example, instead of 2, you may send 3. And then now you actually have a 1 different and 2 same. Then you think, oh, there was an error in that information the sender sent. And also, extreme cases, you send 2 copies of the data, and it is about the accuracy and overhead. Okay, so you can improve the accuracy by sending more copies, but definitely the overhead, right? The receiver only get one information by sacrificing, in this case, 2 copies of that information. Okay. Okay. So now so when we see some kind of specification, like a fiber or Ethernet, there's some kind of specification that this, provide, this bit error rate. Okay, so this fiber provide 10 to the minus something error rate, things like that. So based on that, how you compute the packet error rate? Okay, so let's see. So suppose that we're sending n bits. Okay, so probability of the bit error is just with PB. Then if we assume that some independent bit errors, so then, probability of packet error will be the, probability of at least 1 bit corrupt, right? Even 1 bit corrupt, you have, the packet error. Even you have a whole bit error, packet error too. So which means so this one you flip it, then 1 minus the probability of every bit is clean. Is the probability of the packet error, right? So this 1 minus PB to the n. So one example. Okay, so I read some kind of specification. This medium has a 10 to the minus 6 bit error rate. Okay, and then now I'm computing. Okay, I have 10,000 bits. Okay, then what would be the so this is n 10,000 bit. Then what's the 10,000 bit is for 1 packet in this case. Then what would be the probability of the packet error? So if you compute based on this one, then we see around 1% packet errors. So this is just when I made it, 10 to the minus 6. But if you see some kind of optical link, so typically it's less than 10 to the minus 12. So if you compute, then you have a very, very low packet error rate. So that way they achieve very high performance because you have a low packet error rate, which means you can use some different encoding techniques. basically even sending 12 bits and getting 10 bit, or even you're sending 20, you get 19, something like that. More efficient encoding, you can use it. And how about the wireless link we are using? So this is 10 to the minus 3, which means when you communicate, you may have a lot of packet losses. Even you are communicating with this access point that just computing with this one, right? 10 to the minus 3 to there, then you have a very, high loss rate. So that's why in the wireless, that link layer implement a certain scheme to address this issue, because you have a keep, packet losses, right? And then you realize at the end, okay, I sent it, and then, okay.
When you say that a bit is corrupt, is it that like the bit itself has a problem, or can a bit only be like lost or existing when it shouldn't exist?
I mean, both cases, bit can be lost, or because of interference, maybe that
Extra one gets sent.
it is it was a 0, but it could we identified that 1, then it's corrupt,
Okay.
right?
I see. Thanks.
Okay. And also there are multiple error detection techniques. So, parity check is pretty common. So, odd parity and then even parity. So always so 1, 2, 3, 4, 5, 6, 7, right? So, okay, out of 8 bit, we use a 7 bit for information and 1 bit for the error detection, okay? And then our link layer protocol already know that we use odd parity schemes, okay? So when we send it, okay, 1, 2, 3, 4. So I have a 4, 1. So, okay, because I'm using odd parity, so I have to put 1 more so that, number of 1 bits is 5. Okay, I'm sending it. And the receiver receiving it, and then somehow any of these bits, for example, 0 changed to 1. Then you know that, okay, I'm supposed to receive the bits with odd parity, but somehow received even parity, then it's wrong, right?
2-bit corruptions then? Like if you have even parity and 2 of your bits switch to 1 to 0?
Exactly. So that was some midterm question. What's the issue of this, odd and even parity? It cannot detect 2 errors, okay? 2-bit errors. So that's the issue of this, parity, okay? And also, we can apply this, the odd and even parity, some kind of, 2-dimensional. So, for example, you have a data. So you have a data like this, right? And then, okay, I'm gonna use the even parity. So, okay, so 7 bits. Okay, so this is 1, 0, 1, 1, 1, 0. And then also we use horizontally too. So then it's actually using 2-dimension and also detect errors, right? When you're sending sequence of the informations. And also there are some checksum too. So this checksum actually used in the IP layer too. So and then treat data as some kind of 16-bit word. And then, compute the sum. You actually somehow, operate in the sum of the 16 bits. And then also, you combine that information with the packet. And then they also do the same calculation at the receiver. Okay? Instead of just, 0 and 1, you basically, hold, the 16 bits and then calculate. And then you adding those 16-bit word into the packet and sending it. And you do the same computation, then you basically know that whether that checksum is correct or not. If checksum doesn't match, then you discard. You even can discard, or you try to recover too. Okay. And also there are CRC, so you can read it. And then also because so far we discussed error detection. How about error correction? In certain cases, error correction is quite necessary. Okay. So see the simple cases. Okay. So simple technique. We're sending 2 copies of data, and so original data 0, 1, 0, 0, and then sending 2 more copies. Then basically the receiver will receive all 3, right? And then receiver received 0, 1, 0, 0, but another bit already corrupted, right? Because of majority rule, 2 or basically saying 0, 1, 0, 0. So I decoded 0, 1, 0, 0. But in this case, the efficiency is 33%, right? You're sending 3 in order to, sending 1, right? You're sending 3 and the receiver only, use 1. So 33%. And, it actually should be so inefficient. And then also, cannot correct 2 errors. So in case that we have another 1 here, errors, then basically cannot correct, right? Because you may correct wrong, information. Okay. Okay. So since because I just sending 2 copies, seems like it's not really scientific. So let's see. Have anyone heard that FEC, forward error correction? Yeah, I think many of you. So instead of when we're sending k bit, we're actually we're sending n plus k bit. And then when receiver basically can recover this k bit. So it looks like complicated, right? So see. So when we send the 1, 1, 1, 0, 0, 1, 0, 0, instead of, we are sending 1, 1, we're sending 1, 1, 1, 1, 1. And then 1, 0, we're sending 0, 1, 0, 1, 0. And things like that. Then, and then receiver receive 0, 1, 1, 1, 1. So it's actually, there was, yeah.
At the right, I don't understand the 1, 0, it maps to 0, 1, 0, 1, 0.
So we want to sending, 2-bit information, and then we use extra 3-bit, so it's a 5-bit. So instead, so 1, 1, we're sending 1, 1, 1, 1, 1. And then 1, 0, we sending 0, 1, 0, 1, 0. Okay? So how we come up with this one? That's your question?
I think so. I'm.
Yeah. So that is
But maybe I'll follow along.
No. It's actually a good question. So when we design this kind of code, right? You should have a maximum independence. So meaning that. So when we have this kind of encoding and sending it, when even you have a 1-bit error, you always can find the closest one. So for example, here, right, 0, 1, 1, 1, 1. You have a 1-bit error somewhere here, but 0, 1, 1, 1, 1 close to this 1, 1, 1, 1, 1, not anything else. So meaning that when we encode it, you always have encoding such that you even have maximum errors. You have a high probability to decode to the close to one. So that's the way. And then whatever this number, that would be like that, right? So you have here, you even have a 2-bit errors. You still think this is the closest. So for example, so don't need to come up with this one. Okay, this is the example.
Right, I understand now.
Yeah.
I thought that was some. something, some more clear pattern?
No, it's actually a good question. Okay.
Then I guess if I'm understanding this right, it's like it's mathematical how we get the thing on the right. Like basically we add those 3 bits, and then we treat it like a vector in whatever space it is, like n plus those things.
So this is a simple example. So you search Reed-Solomon code and things like that. It's actually there are more operations and more theory involved. Okay, and so for example, this FEC is used popularly. So for example, have you heard any RAID system? Some storage system that everyone use it in the enterprise. So they're saying, oh, if this is actually disaster, this even, you can read even, couple of hard disk failed and things like that. So for example, some RAID scheme that if you have, 5 disks and then even 2 disks fail, you still can recover original data from the 3 hard disk. Okay? So things like that. Or, also there are many other applications. For example, like a link layer. So when you're sending it, because this is a wireless link, it's too much, is losses here. And then, then instead of sending 3 packets, I'm sending 5 packets. But any of the 5 packets, you lost, up to 2 packets, you always can recover. So things like that. So it doesn't have any, even like which packet is lost, right? You're sending, for example, like this. So even the storage, right? So you have one storage, you have, 5 different. Another one. And then you lost here, and then you lost here. You still can recover using 3. And then also you lost here and lost here. As long as you have 2 others, you can recover. So this is one example we use in storage. Link layer like this. You sending 1, 2, 3, 4, 5. Sender and receiver receive it. Still, you recover the original data. So as long as you do not lose more than 2 packets, you always can recover. So this is some example using FEC. So which means that this is a pretty simple example. So you cannot really use for some kind of general application.
Only if the error is 2-bit, there are 2-bit errors like 0, 1, 0, 1, 1. Then it will be closest to the second one, right?
Yeah.
So that means even there are 2-bit errors, then there is also a chance that you won't be able to recover the actual.
Yeah. So this is one example. So it's not, you cannot really, 2-bit, we always can recover. It's not.
What do we do if it's one error away from 2 possible messages? Like if you had 1, 0, 1, 1, 1, that's 1 away from 01 and 1, 1. So
1, 0, 1, 1, 1, and then another one. So 1, 0, 1, 1, 1, and then.
Yes, that could be either the second bit's wrong or the 4th bit's wrong. How does it know which one?
Yeah. So that actually then is the uncertain.
Okay.
Yeah. So this is one example. So it shouldn't be like this one, but yeah, in order to give example, yeah.
But the point is that like the probability of that corruption happening in a way that you couldn't make that distinction is lower than it would be of you not being able to make that distinction, right?
Yeah.
The point is that it's just a higher probability that you would be able to recover it.
Yeah, so it's something like, if you just apply to this kind of thing, then maybe much more easier. So for example, here, you lose, so in this case, up to 2, right?
Right.
You lose any of the packet, that's fine. 1 packet is fine. And then up to 2 is fine. But after 3 is uncertainty happens.
Yeah.
So you cannot really decode which one is correct or not.
Imagine there's some trade-off between the added inefficiency of this kind of encoding and the percentage of errors you expect to be able to correct.
Yeah. So that's why even this FEC that a lot of people propose, based on your loss observed, that you're changing the whether K should be larger or smaller and things like that. The dynamically adapt this whether you have a longer encoding or not, also depending on this loss. Okay. Okay, so let's see. So shared medium, right? So we just briefly discussed so there are 3 ways. One is partition the medium, whatever. You partition the frequency or partition the time. And also, you can do token based. You pass the token, and then whenever, whoever that having token can transmit. And also, you just let them compete, right? So let's see one example. Okay, so there are, this, connect with the Ethernet. And then, Ethernet is a single shared, broadcast channel, right? So then, how are we going to provide the communication for, all of these 3 people? Okay. Okay. So, and then we call multiple access protocol. So multiple access protocol. So providing the multiple user share the same channel. Okay. So one is So for example, a single shared broadcast channel, then you need to make sure that only one speak at a time, right? Either you using time or whatever different tone, and etc. You need some way to do it. And also, the multiple access protocol, when we talk, is basically some distributed algorithm that determine which node can speak. Okay? So for example, TDMA, right? Time 1, you speak. Time 2, time 3, time 4. So frequency, you use the higher frequency and mid frequency and things like that. So that the algorithm determine which node can transmit. So there are 3 different types. One is channel partitioning. So this is more like time or frequency, and another one wavelengths, right? You have different waves, and you also can partition that way too. And using token, and finally using random access. So let's see TDMA. So this is a time division multiple access. So we divide, channel into multiple rounds. Okay. So this is the example. Okay. So we have 60 users. I want to develop my TDMA protocol, time division multiple access protocol, and providing the access to all of you guys. Okay, now is a total, we have a 60, so I created 60 time slots. And then each time slot lasts for 0.1 millisecond, for example. Then now, after 60, then only 60, then 600 millisecond, then another, round begins and things like that. And then, but some of you may not want to transmit anything, right? So that's why, time slot 1, time slot 1, and then this host is sending it. Time slot 2, I don't have anything to send it. 3, 4, and things like that. So now you can see what's the pros and cons of using TDMA. So what's the process?
Everyone will get a slot to transmit.
Some fairness.
And the concept is like at sometimes you may not have anything to send, and you will waste the slot. So that another guy who's waiting to send will have to wait.
Okay, so that is efficiency, right?
Yeah, wastage of
resources.
Yep. Okay. So that exactly. So the so cons is the because you may have many wasted time slots, right? And also see, it's actually similar, the FDMA. So instead of using time, and now we use some kind of frequency. Okay, so we call FDMA, frequency division multiple access. So, channel spectrum is divided into multiple frequency band. So for example, Wi-Fi channel 1 to 11. So when you use a Wi-Fi and then channel, you manually can set, right? Okay, you already know there are lots of people using channel, 9 or 10. You may set, okay, I'm going to use channel 6, for example. So this is more like frequency division multiple access. And this is example. So because you already divided frequency into multiple slots, so anyone actually can send time. But again, also frequency is wasted, right? If someone doesn't send anything, then, for example, these two people doesn't have anything to send, then you basically wasting your frequency, right? The same thing. Another one is wavelengths. So it's a lambda, right? So you have this lambda or different lambda, and then you can have just like a frequency division, right? You use a different wavelengths to communicate with the different peoples. Okay. So now we covered this TDMA and FDMA. Basically, divide your resource either in time or either in frequency or wavelengths. And next one is the using tokens. Okay. So if you don't use a token and then you always polling who actually currently using, and definitely it has some kind of overhead and then also latency and etc. So in case that we use a token, so this actually used the earlier days of the IBM mainframe computers, and their protocol actually used a token based approach. So basically, then you whenever that the certain user need to send in, your token always take the token first and then sending it. So what would be the disadvantage of this approach?
In case if the ring breaks, then the token cannot pass between the two.
Yeah. So if some host already has a token, and then somehow crash it, so nobody returned that token, right? So then whole system cannot really use that token, and then efficiency actually drops. I mean, there could be multiple ways to, for example, you basically set the timeout, okay? When you grab the token and then you don't return until a certain period of time, you think, oh, this actually fails, and then you may grab it. But even that, this has some kind of, it's not really robust to, failures, right? Okay, then now the last one is a random access protocol that we use every day for this kind of protocol. So random access protocol is like this. When node has a packet to send, and then just sending it. And that means you don't need any coordination among nodes. You're sending it. And then now a problem happened, right? You're just sending it. But because, two or more transmitting nodes, then you have a collision, right? So you have, we have 60 users, and then only one, and, not many people sending it, then this may be the best way. Whenever you send it, right? But we have more users, try to sending it. Then now we have more collisions, right? Then how to deal with this collision is, these random access, protocols, the specified, how to detect and also how to recover from these collisions. So one example is like this. Okay, when you're sending it, okay, you just send it, and then see whether, there's some kind of collision happens. Okay, then you may, wait for random time and then try it again, and things like that. That's pretty much, from the common sense, right? So, and then let's say some key ideas. So carrier sense. So earlier days actually even didn't do any carrier sense. You're just sending it. Whenever you want to send it, send it. Your efficiency actually drops significantly when you have more users. Why not we do a carrier sense first? Or we sense first that anyone actually sending something. So this we call listen before speaking. So, okay, we listen first before speaking. And if there is some kind of speaking going on, don't interrupt, right? And then, just like, checking if someone else is already sending data, and then waiting until the other node is done. So this is a carrier sense. And collision detection, then you basically that already identified, oh, okay, someone else is start talking, then you just stop so that don't interrupt, okay? And then also the randomness. So there are carrier sense, and then you also have a collision detection, and then there's also randomness. Is okay when you detect losses. So multiple users might detect the loss at the same time. Then what happened? That you guys use the same backup time. Okay, I'm gonna wait 10 seconds, and then I will access the channel again. And then you all, share the same, number. Then you collide it again, and things like that. So we somehow need to randomize the access, right? So that is a randomness. Okay. So then, this, the random access, right? So the earlier days, Aloha protocol, that just like this. So host transmit whenever have information, even doesn't have any carrier sense. So when you want to send something, you're just sending it. Okay. So then the collision will occur, right? So when two hosts try to transmit packet at the same time, and just assume that we have a one round trip time for an ACK. We're sending data, and then the data, the acknowledge coming back. Then in this situation, that is like this. So collision of packet can occur when packet overlaps another packet, right? So it's like this. So you have this is a time slot, right? So either you may sending packet here too, and anyone join here will collide, right? And also when you may be sending at almost this point too. So anyone sending around this time always will fail because it doesn't have any time that you. So this is not the absolute time. So whenever you're sending it, because you don't carry sense, whatever. So whenever you send it, that is a time slot. But that time slot may be the overlap, two, right? Because one round trip time for one acknowledgement. So whenever you're sending it, that you have other users sending in this two time slot, then you're lost, right? So that's why the up to 2 packet interval that you wasted. So then how to improve it, this one? Because you don't have any slot, right? Because if you have a slot, then maybe much better. Because now you're just sending it, and then your slot just starting from when you're sending it. Instead of that, why not we use some kind of slot so that we don't waste, 2 slots So that is a slotted ALOA. It's the same algorithm, but you always have a slot when you begin. Because when you're just sending it, then whenever you actually can send it, right? So there is no starting and ending of each slot. But if you have a slot, you are only allowed to sending some data at the beginning of the slot. Okay? So now see, like this. Okay, now instead of sending any of this time, okay, node only can send at the beginning of the slot. Okay, so 1, 2, 3, 1, 2, 2, and 1, 3. I mean, definitely, this is much better than the just ALOA scheme because of it actually saving some wasting slot, right? But still, not efficient compared to the CSMA CD that we are currently using. Okay, let's see this. So this is the graph that one is a throughput per frame time, and this one is what is this? 3.0. Yeah, this is the some per packet time. Anyway, so the reason that I'm showing this graph is that some efficiency. Okay, so here, if you see the pure ALOA, because it doesn't have any time slot, so meaning that your performance is like around 18% because you don't have any explicit time slot. But after just adding time slot, so only this whoever wants to send in only can send it starting up to that slot, and actually improving 37%, right? So here's the missing part. Why we do not use a carrier sense? Then this performance will, goes up, further too, right? So that is the CSMA CD. Okay. So now we talk about CSMA. So here, collision hurt the efficiency of ALOA protocol, right? So that's why slotted ALOA, so you always have a node sending at the beginning of each time slot. So it actually could achieve 37% instead of 18%. Then why we not just change this a little bit? Okay, ALOA always transmit before listen, right? It's sending it and then listen it. Why not we listen before transmit something? So this is CSMA. So carrier sense first for multiple access. So, if the channel, the sensed idle, then it transmit entire frame. But the channel somehow busy with other transmission, then defer its own transmission with some random backup time, so that even you have more users, the somehow is actually coordinated. Okay. So like this. Okay. So CSMA. So listen before transmit. Looks like a really good idea. But what happened is that, okay, now B sending data, and then also D also sending data. But somehow B and D are not in the communication range. So basically, whenever that another user finished the transmission, and then B and D start transmitting. Then B sending data to here, and then D also sending data to here, and still they collide, right? Because it's actually there is it takes time to reach it to B as well as reach it to D. So that is also wasted. So CSMA CD basically that you actually there is some time that you basically can detect a collision. Then you just stop transmitting because you already know that there are another transmission going on. So see, the abort transmission. And then after that, wait random time and transmit again and things like that. Okay? So now, so we covered this linked layer medium access. So one way is partitioning. So you either partition the time or partition the frequency or partition the wavelengths, or you either use some kind of token passing and or using random access. Okay? So last one, 1 minute. Because you question, right? So channel partition A, B. Channel partition, is that efficient fair at high load, inefficient at low load, inefficient at high load, and efficient fair at low load? Which one?
B.
B.
A. Oh, yeah.
A. Efficient, yeah, because efficient, right? You have more user transmitting, channel partition is the best. Okay, now taking turns is actually very tricky, this one. Inefficient at high load, efficient at all load, robust to failures.
C.
What?
C.
C? No, it's not robust to failure, right? You remember, token, whoever that, having token fails, then, is actually not robust to failures.
Inefficient.
A. B. You're correct. B. Yeah. So efficient at, because of the there's no other access, right?
It was definitely one of those.
So so efficient at all loads, and but it's low. Okay. Random access. Which one?
B.
Which one?
C.
C. That's correct. Because efficient at low load, right? Because whenever you sending it, and not efficient for all load, right? There are many users to use it. It's not, efficient. So it's a C. Okay. Thanks.
I'm just gonna go. All right.
Oh yeah, I